Hi everyone. In this session we are going to talk about BOD again, but we are going to calculate this parameter for water quality. So we have, if you remember, the BOD5 is measured in milligrams per liter, and we have this first example. In a 10 milliliter sample of wastewater were mixed with enough water to fill a 300 milliliters bottle. The initial OD was 9.0 milligrams per liter. To help ensure accuracy in the test, it is desirable to obtain at least 2 milligrams per liter decrease in OD over the course of the 5 days, and the final OD should be at least 2 milligrams per liter. So in here we have the all the data to obtain the rank of variety of BOD5 that this solution we produce with the desired results. We desire that we have 2.0 milligrams decrease over the course of the 5 days. So we have this data. We are going to put in here so you can see it. First, the data is that we have a volume of residual water or wastewater of 10 milliliters. Then the volume of the bottle is, as you can remember, and standard it's 300 milliliters. Then the dissolved oxygen initial of the dissolved oxygen is 9.0 milligrams per liter, and we have the final DOF of 2.0 milligrams per liter. These two are the delta DO. This is the measurement we have. Then is a max value of the delta, and we have you say in the problem a decrease of dissolved oxygen. Then this is measured like a delta DO. This is the minimum that we have. This is the desirable result is 2.0 milligrams per liter. Then we have to calculate two values for the BOD5. The first value is the minimum. You have in here the formula, and this is the BOD5 is equal to DO initial minus the DO final divided in the fraction. So in here we have the DO initial and the DO final, and this is for the one of the values, the max value. For the minimum value we have already made this operation, so we have 2 milligrams per liter divided in the fraction, that is the volume of the sample divided in the volume of the sample plus the volume of dilution. If you can see here in the data, we don't have the volume of dilution. Then we have to use the volume of the bottle. That's the total volume. You can obtain the dilution volume with a simple mathematical operation, but we can also use such like this is a rate, a fraction. We have in here the total volume as the volume of the bottle. So the volume of the sample divided in the volume of the bottle, and that will be the fraction used in here to calculate this BOD. Then first we are going to calculate the BOD minimal, that is using the desired decrease in the BOD, 2 milligrams per liter, divided in the fraction 10 in the 300 milliliters. You can see this fraction doesn't have any unit because it's milliliters divided in milliliters. It doesn't have any unit, so the units are that the BOD remains in milligrams per liter, and we obtain a BOD minimal of 60 milligrams per liter. And then we calculate again using the formula, but in this case the measurements, the real measurements, this value is a decrease that we desire, and the measurements are the maximum BOD. So we have in here 9.0 minus 2 milligrams per liter divided in the fraction, and we have 210 milligrams per liter. That's the BOD5 maximum. Then the plausible range, it's 60 milligrams per liter to 210 milligrams per liter. So that's the answer of the problem. This exercise is using, if you can see, the analytical experiments also are made by calculating some of the parameters. So in here we calculate a variety of BOD. So BOD also could be calculated as a mixture. If you remember this, these bottles is when we use diluted bacterial culture to measure the BOD of a wastewater sample. So we introduce the sample and the diluted bacterial culture with a reference bottle. Then this is a mixture, and in here we have the formula to calculate any of the parameters that are in here. So BOD M is the BOD of the mixture multiplied by the volume of the mixture is equal to the BOD of the sample that is entered into the flask, multiplied by the volume of the sample. Is W because it's referring to wastewater, minus the BOD of the diluted bacterial culture. That's because we are using D, multiplied by the volume of D. Then here we the value that is of our interest is the BOD of the wastewater sample, because we have an effluent that is from an industrial process, and we have to measure this BOD. So we have this same formula, but the BOD of wastewater in one side of the equation. If you can see also substitute the formula that we saw before. This formula, that is the BOD5 is equal to the dissolved oxygen, the initial, minus the final dissolved oxygen, divided by the dilution rate. So we put this on the formula, and a group common terms, and this new term that is B, it's only for avoid confusion, because we have in here also B is the diluted oxygen, but in this case of the diluted bacterial culture. So I just put it like B to avoid confusion in the DO letters. So this B is the diluted oxygen of the diluted bacterial culture, the initial and the final. And we have in here an additional term grouping the common terms. So if you are asked about the wastewater BOD in a mixture with a culture, bacterial culture, you can use this formula to calculate the sample and then compare it with this chart that is and the standard. You obtain that value for the wastewater, and you can see an indication of water quality with a color. A very good indication, I must say. So the rate of the composition of the organic matter is proportional to the amount of waste that remains in the flask. So if you can see this behavior can also be expressed as the exponential decrease in biochemical oxygen demand. So this equation and this one is just considering a linear mathematical method to measure this BOD sample, but this sample also can be represented by a math model that is a first order chemical reaction. So it's represented mathematically as the equation 1. You can see here the differential and a constant value, and L, that is the oxygen demand in time, in a time t. Solving this equation, that means using mathematical process to eliminate the differential. We have this, we pass the differential to the other side of the equation, and we have the total oxygen demand in here. It is equal to the carbon total oxygen demand and an exponential. If you can see here, if BOD is a first order chemical reaction, it has an exponential behavior. So it could be defined also like equation 3, and we have in here the BOD in function of time. So leaving the BOD in one side of the equation, then we have this formula in the equation 4. If we have the graph for this equation 4 formula, you can see in here the exponential model decay. The decay model is in function of time. So the BOD is content in the flask is going to decrease like this. So if you have some scales in here, you can see which are the values for BOD through time. Well, this is exercise 2. We can estimate those values of oxygen demand diluted in the flask from the values of BOD 5. So the problem says the dilution factor P of an uncultivated mixture of waste and water is 0.030. So you can see here that it's a mixture of waste and water, and the diluted oxygen of the mixture is 9 milligrams per liter, and after 5 days it decreased. We have in here another delta to 3 milligrams per liter. The reaction rate constant is known to be 0.22 days to the -1. So you can see these units maybe are not common, but we have always this kind of units when we are using a constant value, because it's used to obtain the correct units for all the equations. So they are asking us what is the residual BOD and what is the LO. This is if you remember, the LO is a carbon total oxygen demand. So what is the BOD after 5 days? We have the data. They are giving us the fraction 0.030. See here, you see the dilution factor is blah blah, and you have in here the mixture without culture. You remember this is the formula, and we have in the data also the initial 9 milligrams per liter, it's this one, and the after 5 days, so is the final OD is 3 milligrams per liter, and the BOD should be said D here. BOD 5 is unknown, the constant is 0.22, and then the inverse of the days, should say days in here also, and we have the total carbon diluted oxygen unknown also. So using this formula, we substitute the values, and we obtain a BOD 5 of 200 milligrams per liter. And from the other formula of the exponential model decay, the decay model, we have this, we put this unknown value on one side of the equation, and we have the BOT in 1 minus the exponential. So we have all the data. The time in here is easy because we already know that it's 5 days, because we are calculating the BOD 5, so it's 5 days always. Constant value plus the 5 days, and we have the residual BOD would be, we had in the as the initial value 300 minus 200 that we obtain here by the BOD, and then this is equal to 100 milligrams per liter. So the results are the BOD 5 are 200 milligrams per liter, the total carbon oxygen dissolved is 300 milliliters per liter, and the residual BOD is 100 milligrams per liter. So we are talking about diluted oxygen, but we are not calculated the diluted oxygen. So we have in here the theoretical oxygen demand. This is a pure calculated value. The other values were calculated as a function of some experimental data, but this one is only theoretical. So if you have a chemical composition of the substance, then you can calculate the theoretical oxygen demand by stoichiometry. So the third example is we calculate the theoretical oxygen demand of 108.75 milligrams per liter of glucose, and then we consider the chemical balance equation. So what we know is that we have a compound and it's going to be oxidized in the presence of oxygen. Then we have the glucose plus the oxygen. This gives us the main products of the composition, that is carbon dioxide plus water, as we see in the past class. And the data we have here is saying us that it is by stoichiometry. We have the molecular weight in grams per mole of the oxygen. You can use all those values from the chemical data. So the oxygen is 16 of molecular weight, carbon is 12, and hydrogen is 1. Then the solution, you use this molecular weight using this equation. How many oxygens you have in the glucose? You have 6 oxygen, then 6 plus molecular weight, 6 plus 16 is equal to 96. Then how many carbon you have in the glucose? This is the formula. 6 carbon plus 12 of the molecular weight, you have equal to 72. Then the same thing for the hydrogen. 12 plus 1 is equal to 12. Then you made the sum of these three components, and you have 180. And you do the same for the oxygen. You are using only the products and the molecular weight of each element to calculate this. So the oxygen is going to be 6 plus 2, and you have the molecular weight of the molecular oxygen. Then there is 192 grams of oxygen are needed to oxidize 108 grams of glucose to carbon dioxide and water. This is a factor of conversion that we obtain in there. So we use the initial data of glucose in here in milligrams per liter of glucose, plus this factor that we calculated through stoichiometry, 192 grams of oxygen divided in 180 grams of glucose, and we have in here that this remains as 160 milligrams per liter of oxygen. So we converted the glucose in oxygen using stoichiometry from the balanced chemical equation. Then the result of the theoretical oxygen demand for specific this 108.75 milligrams of glucose will be 160 milligrams per liter of oxygen. So we studied three methods of calculation. If you remember, we are calculating first the BOD of a wastewater sample. Then we calculate, well, in here you have another example of BOD but with a culture of bacteria, and then we calculate a BOD as chemical reaction of first order, and finally we obtain a way to calculate theoretical oxygen demand by using stoichiometry. That will be all. Greetings.